Let A be the matrix shown here. We are going to show that A is orthogonally diagonalizable. In other words, we are going to write A as U times D times U transpose, where U is orthogonal and D is diagonal. So the characteristic polynomial of A is given by the determinant of this matrix here. And we'll use the cofactor formula and expand the determinant along the first row. So the roots of this characteristic polynomial are 0, 9, and minus 9. And so the eigenvalues of A are 0, 9, and minus 9. Because the eigenvalues are all distinct, we can diagonalize A and then normalize the eigenvectors for the eigenspaces. Now we're going to set up a table here. The first column will be the eigenvalues. The second column will show the reduced row echelon form of the matrix A minus lambda I. And the third column will show a basis for each of the eigenspaces. So for the eigenvalue 0, we are just looking at the null space of A. And the reduced row echelon form of A is given by this. And a non-zero vector in the null space of this matrix is 1, 1/2, 1. But then we need to normalize this. So we're going to take U1 to be 1 over the norm of V1 times V1. And the norm of V1 is going to be the square root of 1 squared plus 1/2 squared is 1/4 plus 1 squared, so that's plus 1. And V1 is 1, 1/2, 1. And so this is 1 over the square of 9 over 4 times 1, 1/2, 1. And that's 2 over 3 times 1, 1/2, 1. And so we are taking U1 to be 2 over 3, 1 over 3, and 2 over 3. Now for the eigenvalue 9, the reduced row echelon form of A minus 9 times I is this. And so a non-zero vector in the null space is given by minus 2, 2, 1. And we're going to take U2 to be 1 over the norm of V2 times V2. And if you work this out, you'll get minus 2/3, 2/3, and 1/3. And finally, for lambda equals minus 9, the reduced row echelon form of A minus lambda I is this. And a non-zero vector in the null space is given by minus 1/2, minus 1, 1. And we will take U3 to be 1 over the norm of V3 times V3. And if you work this out, you'll get minus 1/3, minus 2/3, and 2/3. And so we can set U to be the matrix consisting of U1, U2, and U3. And so that's the matrix 2/3, 1/3, 2/3 in the first column, minus 2/3, 2/3, 1/3 in the second column, and minus 1/3, minus 2/3, 2/3 in the third column. And for the diagonal matrix D, I'm going to have 0, 9, and minus 9 on the diagonal, zeros everywhere else. And with this, one can check that U times D times U transpose is A. And so A is orthogonally diagonalizable because U transpose is equal to U inverse.